Sorry, I was just trying to.
We don't share it.
I can share it, but they're gonna see the two slides. Okay.
Thanks everybody for coming in that unusual time. Today we have Jed Pixley coming from Rutgers, where he's an associate professor. He received his PhD in 2014, I believe, at Rice, and then moved to a postdoc at Maryland. And he joined Rutgers in 2017, where he is ever since. And Jed is very well known in quantum condensed matter, doing many wonderful works in superconductivity, heavy fermions, twisted materials. And he is known for unusual breadth of his methods and subjects. He is doing both magnetics, analytics, collaborating with experiment, and many other wonderful things. Yeah, please.
Thank you, Alex, for that very nice introduction, and thanks for everybody's patience and me arriving here with 3 tries. I'm here, so I'm very happy to be here. And yeah, today I'll be talking about our work, basically on transition metal dichalcogenides, on finding strongly correlated phases in these systems. And let me just start by thanking everybody who did this work with me. This really was a collaboration very strong with Daniele Guerci. And we were so close collaborating. And then I brought in my group, my student Kevin, and our group postdoc Daniel. And we collaborated for a lot of cast of characters from CCQ that was really led by Andy. And I'm very, very thankful for a lot of discussions with Eva, and I'll show some data at the very end on some exciting direction I'd just want to point out at the very end. So this talk is really going to be on MOT2 WST2. I was asked for an extended introduction. And so I decided to give a more of an introduction into 2D materials and Moray. Hopefully this is informative and helpful. Okay, so I'm going today. I'm going to start with some motivation background, and I'm going to motivate why we want to control correlations so we actually maybe solve problems that are still outstanding in the field today. I'm going to try to motivate a platform to do that is the stacked and twisted transition metal dichalcogenides. Okay. And as I'm saying stacked because I can use 2 different materials, and stacking is enough. I don't have to twist, and I'll explain these details as we go along. And really focus on this heavy fermion emulator in this limit where you can tune this density continuously, and the experiments gave us a lot of surprises beyond the original theoretical predictions. Okay, so from a very broad strokes, my work very much is focusing on quantum phases of matter. We're thinking about phase transitions that are happening in the many-body wave function. So these are sitting at t equal to 0, even though in reality all experiments are done at finite temperature. These universal properties across these phase transitions can affect finite temperature systems. And so we're thinking really about h bar equals 1 transitions here, and these are driven by quantum fluctuations. It could be metal to insulator, it could be superfluid to Mott for bosons, and so on and so forth. Okay, and so some of these we understand really well, and some of them we are still working very hard to try to comprehend, and I'm going to try to outline the ones first we understand well, and then I'll get into the ones we don't. Okay, so if you want to combine this with thermal phase transitions that we all understand reasonably well, or we're very familiar with, at least from our everyday life, is going from a thermally disordered to ordered phase by spontaneously breaking a symmetry. It could be time reversal, it could be U1, it could be a translation. As I also said in the previous slide, we have quantum phase transitions. I could be tuning a parameter of the quantum Hamiltonian, and I could be disordering the system, melting it from quantum fluctuations as opposed to thermal fluctuations. And you can put all this together. We have a critical temperature that vanishes at 0 temperature, a so-called quantum phase transition. This dashed line is a crossover scale for quantum coherence. Above this, thermal excitations destroy quantum coherence. But what's really remarkable, and kind of what I pointed out in the beginning, is that even though I'm thinking about 0 temperature phenomenon, in this quantum critical fan, physics is universal and dictated by the quantum critical point sitting down at t equal to 0. Okay. And I would say that for generic interacting bosons or magnets, I would say that this is a reasonably well understood picture, and it's really successful in describing the phenomenology of experiments. Okay. And here, let me show you an example of one. This is an insulating quantum magnet. TLCuCl3 is a beautiful system. It can be tuned with pressure or magnetic field. here I'm showing pressure tuning, and they can realize these classical and quantum phase transitions, and this is neutron scattering, and they can see the two different universal critical exponents of the two different transitions, the finite temperature classical transition and the zero temperature quantum transition. Okay, so I'd say this is really a remarkable feat of our field that we've been able to really understand these types of transitions, but there are several situations that go beyond this and that we're really struggling to understand today. I would say the prominent example, which my PhD was based on, I'm still thinking about, is that these phase transitions involve itinerant electronic degrees of freedom, and so you have metallic phases on both sides, and you get some sort of strange metal behavior in between. Or if we have some sort of topological degrees of freedom, where there's not a local order parameter that describes spontaneous symmetry breaking, this can also then defy this picture. Okay, and I say that these two, the directions are really kind of the cornerstone of understanding quantum criticality in our modern sense. Okay, so this is going to be the one we're going to focus on today, these itinerant electronic degrees of freedom, though at the end I'll involve topology as well. But I'm not going to talk about the transitions per se. Okay, so let's think of now, this is now an itinerant phase transition. So this is an example of a heavy fermion metal. It gets this name just because the effective mass of the charge carriers is about 1,000 times the mass of an electron, dressed by the magnetic interactions in the system. And here, the color is the resistivity exponent. So strongly correlated, everybody shows this picture, it's pretty famous. So blue is a metallic, P squared. So I have a metal over here, a metal over here. This is actually a antiferromagnet, so it's broken time reversal symmetry. And then you go through this transition as applying magnetic field, and you'd have this linear in temperature resistivity that defies a simple explanation using metal, in terms of a metal. But moreover, what's really amazing about this transition is if you look at the size of the Fermi surface on one side and the other, so this Hall number is proportional to 1 over the charge carrier density in a Fermi liquid. As I showed you here and here, I have a reasonable Fermi liquid, so I can associate this to the size of my Fermi surface. And as you can see here, I'm going from a large to small Fermi surface where the electrons and the local moments become part of the electronic liquid because of that strong coupling situation. Okay, and describing this change in the Fermi surface along with this symmetry breaking is still challenging the field today. Okay, and the reason is there's really no small parameter. It's a very hard problem to solve. Several people here have made significant contributions to this problem. And I'd like to take a different angle, actually. And I'd like to use my experimental colleagues to help me solve this. So if we could control correlations, so if we could actually have a system, so all the systems I just told you about are just strongly correlated. You can't control those correlations. But if we could, then we could engineer systems to try to solve these problems for us by doing the experiment in a controlled fashion. So the idea that I'd like to put forth as a hypothesis would be, can we find readily tunable platforms to turn on and off the correlations so we can try to find situations that have these non-Fermi liquids, and we can study them in detail in experiment and come back with the theory and go back and forth to really try to solve these problems, okay? And I think with 2D materials, we are starting to get to the point where we can really go back and forth and hone these models and really get a full understanding of the physics. And so I'm quite optimistic that in our maybe 10, 15 years, we're gonna be able to solve these problems. So the cornerstone for this came with twisted bilayer graphene. And it was basically taking weakly interacting semiconductors and how do we make them strongly correlated? And so let's start by just putting them together. So if we stack 2 sheets of graphene, the low energy configuration is so-called Bernal stack graphene, AB stacking. I'm showing here, that's the low energy configuration. And when you bring them together, they start to tunnel with a strength W. But in reality, the experimentalists could have also aligned it and twisted it and put it down at an angle. So in addition to the tunneling, now we have a twist angle. And I took a special twist angle here, which is so-called commensurate, meaning that the moire pattern that forms is a commensurate one, and I have translational symmetry on this new moire pattern. If you're thinking about electrons tunneling on this new lattice, you have to go much further. An electron tunnel is exponentially suppressed in distance, and so your kinetic energy is going to be suppressed significantly in this system relative to the interaction scale. Okay, so how do we see that mathematically? So you have a Brillouin zone describing the electronic band structure in the material. For a single sheet of graphene, I have a Dirac cone at K, so I have a linear dispersion, massless Dirac fermion in 2D with a helicity, the opposite helicity at K prime. A physical rotation is going to rotate one of the Brillouin zones, so let's do that. Okay, and I'm doing this, I'm exaggerating this for visual clarity. Really, it's a small twist angle limit, okay? And when you do this, you see that the leading momentum scattering is going to be between these two layers of the same helicity. So you can start building models now for the two Dirac cones. Okay, this is just a rotated Dirac cone. That rotation doesn't matter until you couple them. And once you couple them through this tunneling, you see that leading momentum exchange I try to draw here, actually, there's not just one of them, there's three of them, and that's because there's three equivalent K points in the beryllium zone. So I can shift my K point to the other K points. So I have these three momentum exchanges I have to take into account. These momentum exchanges actually make the problem pretty non-trivial, even in the single particle limit. You have to basically do perturbation theory in this interlayer tunneling in a systematic way. And this, what I'm showing you here, would be building out a matrix in this Q space that you could diagonalize to do this perturbation theory efficiently. You could also do it diagrammatically, and so on and so forth. But this is then the first kind of introduction of the idea from Alan McDonald and Bistritzer, Rafi Bistritzer. So you do this calculation, okay, and you find a velocity. It's given by this rather elegant formula here, where alpha is just the ratio of the tunneling to the twist angle. And you can see that this is a C3 symmetric system. So this is it depends on the symmetry, but the notion of magic angle is actually quite general. And my work some years ago was on generalizing this notion of magic angle, and that's how we brought it to superconductors and so on and so forth. But I'm not going to talk about that today. So focusing on this magic angle, you actually do the calculation, not perturbatively. You can do this numerically. You find this very flat band in the density of my density of states. So you see this sharp peak in the density of states. There's no more modern calculations. This was 2011 that actually allow the atoms to relax on this atomic structure. And then you open gaps on both sides. You can get this very nicely isolated flat band. Okay. And the intuition now is you quench the kinetic energy. So whatever interaction scale that was in the system has to be enhanced relative to that kinetic energy scale. Okay. That's the idea. But it took a long time for that to become reality. And so what happened, where am I? There are several advances. Well, of course, there's the discovery of twisted biographene, my colleague Eva. And then the mechanical exfoliation, this was in CBD gram graphene. There's mechanical exfoliation allowed single crystals to then be exfoliated and have really nice 2D sheets. The problem was still using silicon dioxide as a substrate. It traps a lot of charge, introduces a lot of charge disorder. Then hexagonal boron nitride was discovered as this amazing substrate. Okay, it removed all the charge disorder, and now you have the so-called Terence stack approach, where you can take a sheet of graphene, rip half of it in half, and you can actually know they're aligned, so you can twist them, and you can twist them to within 0.1 degree accuracy. It's an amazing experimental feat. Okay, so now you make the measurement of the conductance in this device I'm showing here, and this is where I had these band gaps from the just single particle physics. You see them here. Okay, this is an empty miniband, full miniband. These are just different twist angles, but they're all around 1.1 degree, which is the predicted magic angle. But what's amazing is these insulating states at half integer filling fractions, which are not due to single particle physics. These have to be due to interactions. There's no other ways to get those insulators. So this was a conductance measurement. They had to then make devices to measure resistance, 4 terminal devices. When they did that, they realized that right nearby is a superconductor on either side of this insulator. Okay, so very good. Looks like we built our strongly correlated system. Let's now look for this non-Fermi liquid scaling. Okay, and it's going to tell you where this field's at in this regard now. So looking across this insulator, you can look at the resistance, and you see several now groups have seen like a linear T resistivity. Okay, so this is resistance versus temperature. And there's roughly a regime where it's linear. So these authors say this is due to strong correlations. These authors say it's due to phonons. Okay, so there's really no way to right now ascertain if this is a strongly correlated effect or if this has a phonon-driven mechanism in that regime of temperature that sees to be linear. And so, from my perspective, I think the system is incredibly interesting, but it's still not sufficiently strongly correlated. Yeah.
The white frequency is no.
Yeah, but you have a very, 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 very small Fermi surface.
Right, but still, isn't that linearity when temperature fluctuates and the white frequency only?
No, but you can tune the point of my understanding of Andrea Young's is that you can tune the Debye frequency, and you basically are not you're not tying it to the linear T. Their claim is that you're playing with the phonons, and that's how you see the change in the resistance. That's the claim of this paper. I would just say that it's not settled. That's kind of my point. Yeah. I think further work needs to be done. But you can see that you don't get this huge linear T resist. You can't. It's a system that's a totally different energy scale. But yeah, I'm open to, yeah, absolutely. My point, yeah, I didn't want to get into this. More of my point, I didn't want to work on it. I wanted to find a system that was more strongly correlated, actually. That's the idea. But those systems are going to come with more disorder. So, c'est la vie. Okay, so let's go on. Are there any questions on this kind of basic beginning on trying to tune correlations? So I'm going to move away from graphene. And I'm going to try to convince you that 2D materials have a lot of room to go. So let's look at this paper, 2013, okay? Van der Waals heterostructures, where they're imagining they could stack based on all these different types of 2D materials. You can design devices with different functionalities by placing different materials in there. And they even had this dreamscape section with Legos, okay? And if you actually, Legos are too restrictive because you can't twist them, right? So their dream wasn't even big enough, But the thing is now we're at the stage where this is really a reality. And the similar, I guess a little bit later, the group of Mazzari did this ab initio, basically estimate of all possible materials that could be exfoliated. So they find materials that are effectively 2D. They find the binding energy, which can be broken by the Scotch tape adhesive scale. And there's about 1,000 material candidates. So I'm only talking about graphene and a couple of TMDs, but there's a huge number of possibilities here. And my group right now is actively trying to predict what type of materials to try to stack and twist in the future. Okay, and that requires machine learning and all sorts of sophisticated methodologies that we're trying to develop. Okay, but now we're at a stage now where you can take, graphene TMDs or two different TMDs. So we have the so-called homobilayers, means you're stacking or twisting the same material. Heterobilayers take two different materials. You also have multi-layers. So there's the trilayer graphene, and there's experiments done here on superconductivity and twisted trilayer. And there's also all these other examples I'm listing here. And what we've gotten from this is an amazing range of phenomenon. I would say that from my perspective, being when I was a graduate student in condensed matter physics, a lot of the phases that we're seeing in experiment now were theorist dreams, I'd say 15 years ago. But it's really amazing to see where the field has come. So we regularly see superconductivity reproduced. There are Mott insulating states, or also symmetry broken insulating states. We have very clear orbital magnets with quantized responses. This is made purely out of carbon. Okay, it's pretty amazing. You have an orbital magnet purely out of carbon. You also have, you can make strongly correlated quasicrystals. It's be appearing in Nature Materials in a month now. But you can make a quasicrystal and then put electrons into those bands, and you can see them become strongly correlated in this entering regime, where I think the methodologies we have aren't really even there yet. And we also have fractionalized phases without magnetic fields. So you have, this is twisted MOT2, and there's also rhombohedral graphene, and there's amazing examples now of this. So while there's this wide variety of phenomenon, there's still a lot of strongly correlated materials we don't understand, and we'd like to have emulators to try to attack them, or maybe discover new phenomenon along the way. And so I'd like to basically put forward is like more or less maybe my hypothesis in this talk is I want to think about using these TMDs to just maybe discover unexpected phenomena along the way, but actually to try to solve old problems in the field. Yes, please. In twisted tungsten diselenide, two different groups have observed it, yes. That was the first twisted TMD to see it. There's also monolayer TMDs that see it. And twisted niobium diselenide would be you can monolayer get superconductivity in niobium diselenide, and they can twist them as well. And twisted visco, which is what I talked about when I was here, I think 3 years ago. So, okay. So like I said, I think I'd like to come at heavy fermions with these new ideas and these new experiments, okay? And luckily there's experimentalists that are leading the way with this as well. So I told you about graphene. Let me now take you through TMDs as the building block, okay? Set the stage. So TMDs, transition metal dichalcogenides, basically you have a transition metal and two galvanide atoms. And if you look at this, you have a 3-layer thick material now, but if you think of a bird's eye view, it's a honeycomb lattice where you strongly break that AB sublattice symmetry because they're two different atoms now sitting there, okay? But they're even richer than just breaking the sublattice symmetry because they have a large Ising-Snyder coupling. So these are weakly correlated materials. You can do ab initio with rather high accuracy. What you're seeing here is a very large band gap due to the AB sublattice symmetry breaking. This is breaking inversion. You also see sorry, I just said in words. You also see a spin splitting. This is due to Ising spin coupling, which you can estimate then the scale. And if you look at the spin dependence of these bands, K is locked to spin down, K prime is locked to spin up. Okay, so that's called valley spin locking. The valley is locked to the spin. This is important, and we're going to use this to actually measure magnetic properties of these materials. Okay. And so you can think about TMDs as being like graphene with broken inversion and a large Ising spin coupling. That's how like the loose way you can think about it. What's the K dot P Hamiltonian look like? So this is one particular valley. So here's your Dirac cone that you have in graphene. You break sublattice symmetry with about an EV scale, and then you have your Ising spin coupling. Okay. And when you put all this together, you can build a low energy theory. So again, in K and K prime are the two distinct K points. You basically have a bunch of whole bands that are spin valley locked, and you can write down a very simple low energy theory for this that you understand very well. So the building block is understood quite well, and now we can start putting these together and manipulating them to try to get correlated states out of them. Okay. So as I said, there's homo bilayers. So if I have two of the same material, I don't have a lattice mismatch, I just have a twist angle. But bringing in two different materials, you have the fact that the lattices are not the same lattice constant and a twist angle. And that also produces a Moire pattern. So your Moire length now is set by the lattice mismatch and the twist angle. And so in these hetero bilayers, you can't get basically a massive Moire scale. You just hope that it's big enough to get interesting phenomena. And in the case of what I'm talking about today, MOTU2, WSC2, it's about a 5 nanometer Moire pattern from that lattice mismatch, which is sufficient. And what I'm showing you here is basically just like in twisted bilayer graphene, you might see these maps A, B, B, B. This is metal to calgenide atoms. So metal, 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 calgenide, so on and so forth. But it's a very similar labeling procedure. Okay, so now we're going to do a similar game here and build a low energy theory. And so if I think about a monolayer of one of the sheets, say with the smaller lattice spacing, it's going to be like this. And then if I have the other lattice spacing, it's going to have a different Brillouin zone size, right? And so I'm not twisting, I'm just stacking, okay? And now what you see is if I stacked AB, so this is AB stacking, meaning I rotated the top one 60 degrees, so that spin down aligns with spin up. This is going to require a spin flip scattering, and you can then build mini Brillouin zones by this scattering process, okay? But in reality, this scattering process is actually simpler than graphene because of the following. It's basically because you can, as first order, you can just treat one potential from one layer on the other. So here's this whole bands I told you about. Here's now the potential from the bottom on the top, the potential from the top on the bottom, and here's the tunneling. And here's this out of plane displacement field. There's an electric field out of the plane, which is an amazing tuning knob because it allows us to move the top of the bands around. So by tuning this, you can move the top of one band relative to the other. You can separate them and you can bring them together and hybridize and have them interact. This is essential, actually, having this displacement field. And now when you do a simplified approximation, which was the first thing that was done by Feng Cheng et al., basically ignoring this interstellar tunneling, basically arguing there's a spin flip involved, you can just write it down as a potential. And the potential then inherits just the many Brillouin zone scattering wave vectors. And you can then basically one-erize these models because there's no topology in a monolayer, and there's no obstruction like there is in TBG. Again, it's simpler, so you can build very nice basically 1A functions, and you can build Hubbard models out of them. And here's them, the Hubbard model parameters is T and U. And the takeaway is that T varies like theta squared, and V varies like theta in this case of twisting. And so you can basically make that very small and have the interaction dominate, okay? And what they did to demonstrate this is they took MOT2, WSC2 at filling 1, and they tuned this through a Mott transition in a continuous way. This is a triangular lattice. I think this is an amazing experiment in many ways. So you have a triangular lattice, and this is filling 1, okay? And you plane this out of plane displacement field. You can see at the single particle level that changes the size of the 1A function. So it can make them very narrow, make them very broad. So when they're very narrow, you get insulators. When they're very broad, you get metals. You have a metal insulator transition, which is actually continuous. So this Mott transition, there's no hysteresis. and you have critical properties consistent with the Mott transition on the triangular lattice. And here's just a conductance map. Here's the two different gate voltages. Here's your Mott insulator. There's a quantum anomalous Hall state sitting over here, so you can have a Mott to topological transition. You can also have metal insulator transitions. This is a pretty amazing setup. Okay, so this got me really excited. When I had these continuous Mott transitions, I got really excited in this material. And they had this really nice review article at the same time, which allowed you to really, please.
It's insulator, definitely. It's metal insulator transition.
Absolutely.
Then you ended to work more.
I did.
What the hell?
They see no signs of symmetry breaking, though that doesn't mean that there's not some sort of magnetic signal they can't measure. So they have, I'll talk about it a little bit. There's this so-called magneto-circular dichromism in these TMDs, and you can use that to measure ferromagnetic signals. But an antiferromagnet they couldn't necessarily discern. So they, you know, to the best of their knowledge, it's Mott. But yeah, I can't say much more than that, as you know. But they see no signs of symmetry breaking, whereas in the TBG insulators, there's now signs of symmetry breaking in all of them.
Mhm.
So, okay, very good. So there's this really nice review article if you want to get into this. And here's the takeaway I would say. So you can compare twisted bilayer graphene to these TMDs. This is what I've been telling you about. So in TBG, twisted bilayer graphene, there's this magic angle. In these TMDs, there's a wide range of parameters where things are interesting. So you don't have to fine tune it so much. It's a bit simpler. You can build Hubbard models more naturally. The spin value locking makes things a bit easier. It also gives rise to topology more easily, as you'll see. And this bandwidth and interaction is much, you know, the bandwidth can be smaller, the interaction can be bigger than in graphene. So this can be a much more strongly correlated platform than TBG in principle. Okay. So with that, I'm going to move on to this emulator. So these are like my building blocks, and I want to do something new with them. And so as I mentioned, I can tune this displacement field. So right now I'm sitting in this Mott phase, and nothing's in the tungsten band, let's say, and I have a lattice of local moments. And now I want to start doping the tungsten band. So I can, experimentally, you can selectively gate one layer or the other. So you can hold MOTU to it filling one, and you start gating WSE2, filling it with electrons, okay? So if you're familiar with strongly correlated systems, you'd be thinking of a Kondo lattice because you're putting electrons into this Mott insulator. And I'm going to show you first experimental evidence that through all this, and then I'm going to show you our theory, okay? So here's how the experimentalists thought about it. So here's their displacement scale. This is filling. So down here is going to be like the control, okay? Down here is going to be a non-correlated system where you fill MOTU with 2 electrons, so it should be a band insulator. Here is the Mott insulator of MATU2. So here you should see strong correlations, okay? If there is. But this one is the control, all right? And you can basically think of these as 2 different bandwidths. And what you're doing is you're bringing this tungsten band inside here so they can hybridize with MOTU2. It's like an intuitive way to put it, as Phi would say, I guess. So here's how now some evidence, excuse me, some experimental evidence. So here's the coherence temperature, where you get the maximum of the resistance, and it curls down with a nice T-squared, okay, over this range of density. You can now compare the coefficient, this A coefficient, and the resistance, which is related to the effective mass of the charge carriers, or the square root of it is. And in the case of 1 plus X filling, you get a very large enhancement that grows with decreasing X, whereas in 2 plus X is completely independent, okay? This is basically the band insulator, the heavy Fermi liquid, right? So this is the first signature of a strong enhanced T-squared coefficient, but they also get the Fermi surface jump as a function of magnetic field. So here's now the Hall number, okay, sorry, Hall density, and you're tuning magnetic field, you're going from filling 1 plus X to filling X, and you polarize. So this is not exactly the thing I talked about in a second ago. I'll talk about that in a little more detail, but this is a jump of 1 whole for more a unit cell. This is really a signature of this is heavy Fermi liquid, and I think there's no really other way to capture this phenomenon, though if you have a way, I'd be very interested to hear about it, actually. There were some other papers challenging this, and they could not capture this, okay? So, because you can get the T-squared a lot of ways, and you can with disorder but you can't get this. Okay. And my postdoc advisor, for example, tried to argue that it was disorder, but I don't think that's correct. That's right. So very good. So I just want to make this one point here. that this is different than the strange metal. So this is a quantum phase transition, and the spin polarization scale is out here, okay, much larger field. So I just want to make the distinction that the Fermi surface changing transition I told you about before is not the one I found yet, okay? This is not, I'm still not there. This is the spin polarized phase, okay? Now they go to low doping, where we expected to see some sort of antiferromagnet. And what you see is an insulator, okay, not a metal. We expected to see an antiferromagnetic metal, as I'll tell you about the theory in a little bit. And what they actually can measure the so-called, basically you can measure a ferromagnetic response as follows. So a magnetocircular dichromism is basically measuring the difference in the right and left polarization of light. One polarization of light couples to K, the other couples to K prime. These are spin selection rules in the TMD. So right circular light only couples to one valley. Okay. If you have a valley difference, valley polarization, it picks up a signal, but you have spin valley locking. So spin is valley. You see, so the signal is proportional to the magnetization. They can't determine that absolute scale. They don't know the proof factor, but they can measure the magnetization. So from that, they can, and this is all been applied magnetic field, so they can measure susceptibility. And this is a ferromagnetic susceptibility. So they have a ferromagnetic insulator of heavy Fermi liquid. But even richer than that, when they put it all together, which is here, so we were expecting some antiferric metal to heavy Fermi liquid. They're finding a ferromagnetic insulator. So this is this TC that they're able to pick up. But down here, they actually have some antiferromagnetic Curie-Weiss temperatures. So the black are the Curie-Weiss temperature. Those are basically telling you the sign of the exchange constant. And so it's, you're thinking it starts from antiferromagnet, becomes ferromagnetic, and then transitions. Okay, so this is what I'm after. I want to try to get this whole thing. Okay, and my first theory is going to fail, and we're going to build on it. Okay, so here we go. So we start building basically a Hamiltonian on the Moiré scale, similar as I told you before. And so you can, yes, please.
So you're saying that you're going to describe transition from heavy Fermi liquid to a ferromagnetically ordered state which becomes insulated.
That's right.
Okay, thanks.
Yeah, I'm going to try to argue it. The insulator, I have to argue from, yeah. Yeah, so now you can basically, from the ab initio parameters of the material, you can Wannierize the parameters and build a Hubbard model, Hubbard-like model of the two layers. Okay, these are the parameters that come out. But what's interesting is you have this phase factor, which is due to this Ising-Sperber coupling, and you have this hybridization, this interlayer tunneling between the two layers. And you can now, okay, so right now I'm going to treat this tungsten band as dilute. This is going to bite me, okay, but let's just do this for now. And I'm going to ignore that interaction, even though I necessarily shouldn't. And I'm going to do a Schrieffer-Wolff transformation to get to that Mott insulating limit of the MOTU2 layer. Okay, and so this is what you get out after you do this. So you get some basically Ising-Sperber coupled bands that are around K and K prime. You then have a spin exchange because of the disconcentry Moria arises because you have a spin-over coupling, so you break inversion. Okay, and so you want to basically form an 120-degree antiferromagnet on the triangular lattice, which is what we originally were thinking. And then you have a hybridization, okay? And this is actually where the problem really gets interesting. So the hybridization is a product of these form factors, and this form factor on the honeycomb is, if the dispersion was at gamma, it would be benign. It would just be a constant. But everything's at K. When you expand this guy near K, you get a nodal hybridization. So this is like the pseudo-gap Kondo problem or the P-wave Kondo exchange. And this can give rise to topology. It also gives rise to a Kondo coupling that is proportional to the density. So if you average basically your hybridization function over the Fermi surface, you find that it scales linearly with density. So the density is actually controlling the Kondo coupling in the system. Very interesting property of that P-wave. And then we use some parton mean field theory to solve this. I can get into details if you like, but we have a more sophisticated machinery now using dynamical mean field theory. I'll talk about later on, but you don't have to use partons, but it's a place to start. Okay, and what you find when you solve that mean field is the following phase diagram. So here's what here's the doping. So here's this large heavy Fermi liquid I've been after, sorry, large Fermi surface heavy Fermi liquid I've been after. And here's this antiferromagnetic phase, which doesn't exist in the experiment. So no, that's not seen in the experiment. And I see a first order transition in the parton mean field. Whether or not that survives fluctuations, it's unclear, but let's now focus on this heavy Fermi liquid phase. which it seems to do phenomenologically do reasonably well. And so I can now think about this band structure, which it's definitely heavy. And if you actually look at these gaps have a topological nature to them, but I have other bands crossing the Fermi energy, so it's not going to be topological. But if I went to the Kondo insulator limit of filling 1, so if I could get rid of this band crossing, I should be able to get to the Kondo insulator limit. And because these band gaps opening are topological, I might be able to get a topological Kondo insulator. Okay, so I will show you at 1 + 1. This will be a topological Kondo insulator, but that's getting ahead of myself. Let's just think about the predictions that we can make from the heavy from liquid calculation. So this density tuned Kondo temperature is tied to the density relation to the Kondo coupling averaged over the Fermi surface. And one thing that we're not getting so good is the size of the Kondo temperature. So we basically, these are our conclusions, and it roughly agrees with this, but the scale is a bit off. So the experiment that Kondo temperature is on the order of 10 Kelvin, we get like 2 orders of magnitude below that. But there's been work that's showing that it's probably a strongly mixed valent limit that we have not considered here. So that's an interesting question for future work. If we figure out the scales properly.
And how does it obtain in terms of mathematics? So is it numeric?
This is a part-time mean field, so you have to solve them. So you can do some things analytically. You can do K dot P in the heavy for liquid phase, but the self-consistent calculations are solved numerically.
So this is still every mean field analysis.
Yeah. So yeah,
It's not like self-energy give you a lot of math. There's a difference.
it's just Pullman boson.
Mhm.
Yeah. Yes.
There's something to justify the mean field approximation?
Yeah. So that's a fantastic question. I mean, I think this is a long-standing challenge, and okay, the heavy for liquid phase, I think deep in the phase I can justify it. If that antiferromagnet was correct, I could justify it in that phase, but across the transition, this breaks down dramatically.
Anyway, you got something towards the magnitude off.
Yeah, that you can get right probably in the mean field. That's not a mean field issue necessarily. That's probably the fact that I'm not in the right so-called mixed valent limit. I have my filling of my local moments perfect, and it should probably be more dilute. But that's based on work that's been done. I cited a
So,
paper there.
So you have heavy mass, but you still have 3 fermi.
Yeah, absolutely. You have no dynamical renormalization effects within the model. And so you can't get the transition right. And as I was saying, we have a DMFT now, so we've gone beyond it. But also other methods are very interesting here. I mean, there's probably a lot that can be done. There's some more statements about the heavy Fermi liquid. So you have basically, this is my Fermi surface. And as I was mentioning to you, how do we know these gaps are topological? Well, if you plot the Berry curvature, which is this color, there's a lot of Berry curvature in the Brillouin zone, which can be activated by applying a magnetic field. If you apply a magnetic field, you get a sizable anomalous Hall response, which is also seen in the experiment. And this jump outside the heavy Fermi liquid is precisely what they're basically seeing here. So we can get this spin polarization very naturally in the model, but as you saw, I did not get the ferromagnetism. So what was I missing? Okay, so I want to come back now and I want to try to get the ferromagnetism right. So I actually have to say that I was at a conference, okay, and this ferromagnetism result came out the day before my talk where I had the antiferromagnet. So that night I went and we did a lot of calculations, and that's when we realized that this tungsten interaction can give you a ferromagnetic coupling. Okay, so and then we ran with that, and we have a very nice preprint on this. And so the point is as follows. So I want to put this tungsten the tungsten interaction back in. And when I do so in a perturbative way, so this is the process I have been telling you about so far, to draw it this way. But when I put this tungsten interaction back in, I can now go back and forth with interacting with the tungsten. That gives me this coupling, which if the tungsten interaction is 0, this is just 0. So this is only finite if the tungsten is interacting. So this is interaction in the itinerant carriers, something you never think about usually if you're doing heavy fermions. Here's my antiferromagnetic P-wave coupling. What you can see here, this is ferromagnetic and it's Ising-like. So I have a ferromagnetic Ising coupling. So I put in an electron, it's going to ferromagnetically couple to my antiferromagnet, and it can pull the spins out of the plane. So I can, by doping electrons with smaller coupling, I can make an antiferromagnet ferromagnetic. That's what I'm going to try to convince you of now. So here's my JZ. So I'm sorry, this should be minus JZ. So this is a ferromagnetic coupling becoming finite. Here's just the other couplings. And we can now do this. So what we're going to do now is we're going to treat the local moments as classical. That's just the starting point and mean field. And then we can then integrate out the electrons in the background of this mean field. in this very dilute limit. And what you find is this JZ interaction cancels the antiferromagnet and actually can pull everybody out of the plane to induce a ferromagnet. Okay, so if you now compare with this experiment, this doping transition can actually be right here. No, go ahead.
Not completely good question. You have a SU2 rotate, is it invariant system or not?
No. I was strong Ising-Spinova coupling, very strong Ising-Spinova.
It's all due to Ising-Spinova.
All due to Ising-Spinova. Yeah, if you set it to 0, no. It's a Spinova coupling.
If it's spin orbit is weak, you still get really high. Or it's not.
Sorry, say it again.
Is spin orbit still a small parameter compared to others? Or
It's small, but it's big, and it's of order 0.1 EV. So it's of order like the interlayer tunneling in TBG, for example. So on these scales, it's not small, I think. Yeah, it's a good way to, actually, I didn't think about it that way. That's a good way to put it. Okay, but I want to do something more than this. And so this Anderson insulator, I also have some information that's not in the papers, but this Anderson insulator, the applied magnetic field, it becomes metallic. So it's very fragile, okay? And so what we started thinking about is, well, maybe I get spin polarons, which are these electronic bound states in the magnetic background, which I could just trivially get rid of by magnetic field, because they're going to be destabilized. The bound states will be killed by magnetic field right away, and you can get the metal. And so that's what we started to play with. And so you can take the antiferromagnet, and you can map that to a nonlinear sigma model on the triangular lattice. And so then you can, this is a 2D nonlinear sigma model. You can then couple that to the electrons, and you can get this ridiculously hard problem that we cannot solve. But what you can do is you can take a saddle point, okay? When you take the saddle point, what you actually arrive at is a nonlinear nonlinear Schrödinger equation, nonlinear Schrödinger equation for the electronic wave function. So this guy is psi dagger psi, so you see it's nonlinear. And you have to solve this nonlinear Schrödinger equation for the bound state, okay? And when you do that, well, we did the simplest thing. We set this J perp to 0, which is going to be probably pretty interesting to think about. Oh, please.
The question before, justify taking this approximation. Any reason to think it other than you can solve the problem?
Oh, yeah. I mean, yeah. So in the low density limit, I mean, there's a lot of ways you can justify it, but in the low density limit, there's very few polarons. There's like a single electron problem. So it's very natural. I'm putting in one electron at a time. So then you can ask about this approximation, which was a bit worse because these local moments are big. They're not classical. But if you have a ferromagnetic signal, you can more or less rationalize such a limit. So there are ways of stabilizing, these mean fields in some sense to justify them. Yes, absolutely. But I'm not doing there's not a large N that's rigorously providing it. It's more of like a large S using the experimental insight that's a ferromagnet. Yeah, without the experiment, I would have thought it was an antiferromagnet,
Strictly speaking,
for that one, I was. Strictly speaking, this is infinite S. For the local moments, but the electrons are treated purely quantum mechanically. All right, and now I take the quantum fluctuations of the local moments into account. I go beyond that mean field and you get bound states. Is that okay? Okay. Yeah, so now when you have them interacting, I'm not touching interacting polarons, but basically there's a threshold, and the fact that the magnetic field kills them, you can see very naturally from the spin texture. So these bound states require no magnetic field. Okay. So lo and behold, how do I connect all this up? Let's put it all together, okay? So to get some handle on the strong coupling problem, I'm going to consider a single impurity limit. So I want to think about the competition between these two Kondo couplings, but thinking about that at the lattice level is pretty non-trivial. So let's solve a single impurity limit and try to piece this back together. So if I take a single impurity limit, this gives me an S wave and a P wave Kondo coupling. P wave is irrelevant just because it carries momentum in the coupling. S wave could be relevant if it's ferromagnetic. But as you can guess, as I already showed you, it's going to be antiferromagnetic. And so the ferromagnetic interaction is irrelevant. So the local moments don't bind to electrons at low density. They have to go through a critical value where the P wave Kondo coupling is large enough. And so you find a phase diagram like this for the local moment. So these local spins that I basically, is the best way to put it. If you think about these impurities, these are unscreened. And then if Kondo coupling is large enough, I screen them, okay? And the fact that I cannot screen them down here is because it's a ferromagnetic Kondo coupling at low density. Okay, I hope so this is the single impurity limit. Now I can put everything together, okay? So I have a spin valley locking induced ferromagnet at weak doping. I'm going to put in disorder. I'm going to argue as follows. So the ferromagnet, if I had disorder, I have broken time reversal symmetry. This is so-called Gaussian unitary ensemble. And disorder is a relevant perturbation, and I will localize an infinitesimal disorder. What's is cool about the P wave Kondo coupling is there's no broken time reversal, but there's broken spin rotation symmetry. So you're in the Gaussian symplectic ensemble, which allows a delocalized phase in 2 dimensions. So this metal insulator transition fits perfectly within the Altman-Zirnbauer classification of localization. So that's how I'm getting the localization. I'm not actually doing a calculation. I'm just arguing based on symmetry. Okay. In the last remaining bit of time, I'm going to try to come at this last piece. So this is kind of putting everything together. So I've shown you here is like this is a displacement field that they can tune. They have to get the bands to hybridize to become interesting. At weak doping, we get an insulating ferromagnet. It couldn't principally be a canted antiferromagnet because that signal might be somewhat still in the plane. And we go to a P wave heavy Fermi liquid. And I was alluding to this limit near 1 + 1 as being interesting. So if we go to 1 + 1, so we knew this actually when we first wrote the paper, but we didn't think it could be done experimentally. And then we heard at the previous March meeting it could, and they were doing it. So I'm going to show some data that's not out yet. Okay, but so now if I go to 1 + 1, I get a Kondo compensated semi-metal. So I have electron hole pockets that are compensated. But if I open my boundaries, I have edge modes. Okay, so this is an open boundary on left and right side. These edge modes are signatures that have some sort of topology. If I could gap out the bands, a couple ways to gap them out. One way we did it, we were thinking a lot about interlayer strain. You basically have to break C3 one way or the other. So this is one way we to do it, but Debongen's group also thought about breaking C3 via an excitonic instability. That also might be a natural way to get that. Just want to mention that. But either way, once you break C3, you get a finite quantized spin Chern number, okay, with a nice gap. And this is a topological Kondo insulator. This is a 2D topological Kondo insulator with a Z2 invariant, okay? So if you've been following heavy fermions and all this samarium hexaboride is this 3D topological insulator candidate. It's still debated, okay? And I'm going to show you data now on this. But before I do that, let me just mention, I mentioned this already, that we can do dynamical mean field theory. And so we can go beyond this part-time construction, get this dynamical linearization. So this is showing that this topological Kondo insulator is stable beyond the mean field limit. And here's the spectral weight of these bands that you now have within dynamical mean field theory. And so this is really actually worthwhile because the experiment is now tuning between these regimes. So this experiments now they're tuning from a topological Kondo insulator to a topological insulator to a trivial insulator. And you can't capture this within partons. So this is something we're after right now within dynamical mean field theory. But let me now show you some really exciting data that's not out. So
that transition should be continuous.
So this is so as far as I understand, the topological Kondo insulator, topological insulator is a crossover. And then you go to a trivial insulator. Yeah. So there's a transition here, but there's a very non-trivial crossover between a topological Kondo insulator and a topological insulator that nobody's really studied at all.
So my impression always was that these were like sort of adiabatically connected phases. Like, how do you really sharply define topological Kondo insulator here?
Fantastic. So the temperature dependence of the gap. So again, it's a crossover, so it's not a sharp statement, but you can basically see that in this regime, the gap is strongly temperature dependent. Here it's very weakly temperature dependent. And then in the experiments, they have some other signatures that were, but there are qualitative differences. But yeah, no, it's a great, yeah, I'm thinking about the same questions. So yeah, Kin Phi from Cornell, was very gracious, and he gave a seminar a couple weeks ago at Rutgers, and then he shared this data with me. Okay, so we made this prediction. This is a prediction, not a post-diction, okay? So 1 + 1, there should be a topological Kondo insulator, MOT2 WSC2. So here's the data. So they have a bulk insulator, the clear bulk insulator. They try to see the edge trans. So now this is the quantized conductance, Hall conductance, almost H over almost 2 E squared over H, almost. And then they can start dividing this thing up into pieces, and I think 10 pieces, and then sending current across pieces and picking up fractions of E squared over H. So this is very much what's been done in Mercury Telluride quantum wells as well, and you can reverse it, for example. So the quantization is not that good, there's disorder, but here's probably the most definitive signature is here. So let me show you this one first. So the bulk conductance, if I apply an out-of-plane field, basically along that Ising-Sperber coupling, it does nothing. If I go in plane, it's a very strong bulk resistance. Now you go to the edge state conductance. So the in plane and out of plane have very different gaps when you break time reversal. In plane is big, out of plane is small. And so this is exactly what's seen in Mercury Telluride quantum wells, where the out of plane signal drops dramatically. The in plane signal remains constant over this range. It comes down over a larger range. This is a Mercury Telluride quantum well. It's a 2D topological insulator, quintessential. And look at this. I really think we found a 2D topological Kondo insulator in this material. And with that, I would just like to conclude. And I hope we can move away from samarium hexaboride. We can think about this 2D system and we can really solve this problem in great detail. So with that, I'm just going to put it all together. So show you we have a spin polaron regime. We have a topological Kondo insulator / semimetal. And I showed you some experimental data on that. Okay. So in this very last minute or two, I'd like to just kind of, look into the future, mention how I believe maybe, routes to quantum criticality. Okay. So I kind of started saying I'd love to be able to get systems that can solve these non-Fermi liquid problems. So first, to do that, we need cleaner samples and we need no Anderson insulators nearby. I think this is killing everything we really want, but they're moving in that direction. They're getting cleaner samples, and that's definitely a push. But what about finding quantum criticality that doesn't need a clean sample? So we know superconductor insulator transitions from great amount of work in the past in 2D materials. Here I want to think about this in a moire material. So with EVA, we've been thinking about twisted trilayer graphene, mirror symmetric twisted. It has the largest TC out of all these moire superconductors. They can, applying magnetic field, they can see really beautiful superconductor to insulator transitions. This is out-of-plane field. And they can also do in-plane field, and they can then do basically beautiful scaling collapse. So out-of-plane field, you feel the disorder strongly because your big magnetic loops. So you're going to be dominated by Griffiths physics. The prediction would then be that Z, the dynamic exponent, goes to infinity at the transition, which they see beautifully. You apply an in-plane field. This should be a superfluid insulator transition. Nu Z should be about 4/3. I put that, I don't know if that dash line is that accurate, but anyways, yeah, I think that is reasonable. But the point is that they're reasonably close to 4/3. So in plane, out of plane, you get two different universalities all in one device. And so this is an example of quantum criticality in a moire device with accuracy enough to see universal data collapse. And so I really think the field is going to be moving into this direction in the next 5-6 years. We'll be seeing real quantum criticality and real accurate estimates of critical exponents as we go on. So with that, I'd like to conclude. I hope I've convinced you that 2D moire materials are a really exciting experimental setting. We can go back and forth with our experimental colleagues to really understand what's going on in these systems. I showed you that TMDs are a bit more strongly correlated. You realize topological many-body physics. And I really advocated that stacked MOT WC2 is a nice platform for future work. So thank you all for the questions and for your attention.
Hey, Judge, questions, please.
The twisted trilayer data showed.
I knew you'd like
what is
the data.
What is the like universal resistivity?
The crossing value?
Yeah.
I think it's, yeah, that's a good, I don't know off the top of my head.
Okay.
I can tell you though.
Is it order H over E squared?
Yeah. Yeah. For this one. Kilo.
So it's a kind of overall follow-up question. Yeah, this is a famously extremely hard problem. So what is finding this in moire going to teach us about?
No, okay. Love it. I'm not making a different point. I'm basically saying now we can, with moire, get to quantum criticality we had in other devices. Like we never had really nice quantum criticality yet in any moire device. And I'd say the superconductor insulator transition might be the easiest one to find. So now that we can find it here, maybe we can go to these more exotic ones. That's kind of more what I'm saying. Like this is a stepping stone to get there. But yeah, I agree with you.
Maybe generic question here. All scales are extremely small. Critical field is half a Tesla. When we talk about insulator, when energy gaps are supposedly on the level of fraction of a Kelvin or Kelvin, is it really insulator or how should we view it?
So type 2 superconductor really a superconductor?
Yeah. But it's not like.
No, I don't. I
Let's
know.
use the word more.
I know what you mean. I didn't say that. This is more like an Anderson insulator, right? This is a superconductor Anderson insulator type transition, disorder dominated. And that's why it can still work pretty well. I think that's kind of my point. Because we need cleaner samples to get to the quantum criticality we want.
But you want to go to quantum criticality,
Yes.
which is normally associated with strong interactions, etc. Interaction scales are completely different, right?
Yes.
And we're talking about gaps of order of Kelvin. So it's not that it's more like what you said, it's more like Anderson physics.
Yeah, I mean, that's a good question. I mean, the superconductor insulator transition, it's a disorder Bose-Hubbard and I don't think it's fully settled on that Griffiths transition, but at least for out of plane, this guy. I agree with you. I mean, the scales are small, but actually, in the case of twisted graphene, that complicates it, right? So I think that's part of the question that we have to handle when we go with these problems, to reconcile those scales.
So when you say like this twisted TMD is not quite as clean as we want it to be, do you know if it's mainly due to TMD, the material itself is not as clean as graphene, or is it due to the twist angle in the machine?
So in those materials, that was just stacked. Those were just stacked. There's no twist. So I think it's really much the monolayer cleanliness, the quality of the monolayer.
So if we were to make a sandwich, like for example, stabilizing it with instead of just putting one layer on the second layer with no twist, maybe add the third layer, would that do you think that would help?
You mean clean it up or?
Like just like why the mirror symmetric twisted China graphene helps stabilizing.
Yeah. So okay, fantastic. Yeah, with the TMDs, we're thinking a lot about the third layer. The challenging thing is getting that displacement field to move the third band to where you want. And so that's something that we're thinking quite a bit about. And you might be able to realize like multi-channel Kondo, and there's a lot of directions to think about 3-layer TMDs. Absolutely. Yeah.
More questions? And let's thank Jed again. Jed is here today and tomorrow, and a couple of thoughts and